and welcome to the first mathematical episode of Spark. Today's investigation will be regarding the inherent bias in sample variance estimators and the nature of Bessel's correction to rectify this bias. Population and sample variance are respective formulas that give similar results and are used in the former when a population mean is given and the latter when a sample mean is given. However, despite the many similarities within the two formulas, the denominator of the sample variance is n-1, which is a stark contrast to the population variance's denominator of n. Why is there this discrepancy? This is due to a phenomenon that whenever a sample variance does not have a denominator of n-1, which is known as Bessel's correction, it is biased, which means that there is a difference between the estimator's expected value, which should be concordant to the population variance, and its actual true value. Through investigating examples and generalization, this biasness will be explored through this presentation. Now, let's assume that within a population of infinite values, a statistician was given 5 values of 46, 48, 53, 54, and 57. Unbeknownst to him, the average or the mean of the entire population is 50. Because the population mean is known, an informal population variance can be calculated, which is the average of the squared differences between the sample values and the population mean. As the population mean is known, this is unbiased as it accurately represents the spread of data from the population mean. In this example, it is derived to be 18.8. However, alternatively, the mean of the sample values can be calculated by summing all of them up and then dividing them by 5. This sample mean can be also utilized to calculate another values of variance. To investigate why the variance between each sample value and the sample mean is biased, we obtain the variance using this sample mean. In this case, indeed, when comparing the values, the variance calculated using the sample average is below the variance calculated with the population average. Why is this always the case? Using algebra and generalizations, we will be able to discern why. If we are to dissect the variance using the population average, we are able to prove that the variance calculated with the population average is always going to be larger than the variance calculated with the sample average, meaning that the variance calculated with the sample average will always underestimate the variance from the population average. If we take each squared difference between the data value and the population mean, and we split it into two components, which will be the difference between the term and the sample mean, and the difference between the sample mean and the population mean, we can see that no overall value was changed, that they are still the same but are only decomposed into two components. In this case, the sample mean is 51.6 and the population mean is 50. Now that we have two components that are inside the square bracket, we can expand this bracket using the property a plus b squared equals to a squared plus 2ab plus b squared. Now when we repeat this for the 4 other sample data values, the variance using the population average is shown as below. For subsequent calculations, the population variance will be split into 3 sections highlighted in green, blue, and purple. Let's take the green section first and write it out. Under closer inspection, we realize that it is actually identical to the variance obtained using the sample average. Therefore, the variance obtained with the sample average is going to be smaller than the one obtained with the population average if blue and purple don't sum up to be 0. But first of all, we need to ascertain whether blue and purple actually add up to be 0. So when we inspect the blue section and we rearrange it into common factors, we can pull out the difference between the sample and the population mean and subtract the middle column. However, as the sum of all sample values is equal to the mean of the sample values multiplied by the number of these sample values, they all cancel out and therefore the entire blue section can be commuted into 0. On the purple section, we merely obtain the square of the difference between the sample and the population mean. In any case where the sample mean and the population mean happen to be different, the variance using the population average will be larger than the variance using the sample average. Comparing the two variances, we are able to see that the variance using the population average consists of the variance using the sample average and 2 additional components in blue and purple. Therefore, although blue is always going to be 0, should the values of the sample and the population means be different, the variance using the population average is going to be larger than the population using the sample average, as purple will consequently not be 0. Therefore, the average square of the deviations using the sample mean is nearly always too small to provide an unbiased estimate of the variance using the sample values and therefore is biased. As we have already proven that the variance based on the population average will always be equal or larger than the variance of the sample average, they can be displayed on the number line drawn below. And we obtain conclusively a bias variance estimator as shown on the right, which consistently underestimates the variance of the sample values as proven beforehand, and an unbiased variance estimator on the left, which accurately represents the variance of the spread of the data. You might ask, why not just directly use the population mean? Why go through all the fuss of taking the bias variance estimator on the right and then changing the denominator from n to n minus 1? Well, at the start of the PowerPoint, it was said that the statistician only has data values of a sample of data and not necessarily the whole population. It is impossible to derive a population mean from merely a sample set of data, as the sum of all the population data must be obtained to divide by the number of data values to obtain the population mean. Although in the previous example the population mean was assumed to be known, this is impossible from a sample set of data. Therefore, with a sample set of data, the unbiased variance estimator on the left cannot be used as it requires the population mean. And as we have shown that the biased variance estimator is always going to be underestimating the variance, we compensate for this by decreasing the denominator from the number of sample values to the number of sample values minus 1 to increase the value towards an accurate variance figure. As the denominator decreases and the numerator still remains the same on the figure on this formula on the right, the biased sample variance estimator will increase in value and will thus become closer to the value of the variance calculated if you had the entire population's data values and average, as shown by the arrow linking it to the number scale. So we can see that this will be numerically closer to an unbiased population variance estimator than its biased sample variance estimator counterpart. Alas, when will you ever use the formula on the left to calculate variance? As the population mean must be known, you must have the entire population's data before you can derive this unbiased population variance estimator, which requires a population. Otherwise, to obtain an unbiased sample, you must use the unbiased sample variance estimator for accurate means of calculating variance. Now, you may ask, why do we only have to reduce the denominator by 1? Why not reduce it by n by 2, by 3, make it n minus 2, n minus 3 to compensate for the inherent underestimation? Now, we can simply take the bias estimator and convert it into an expectation form. On the second line, we can add and then subtract the population mean and split the expression into two components, similarly to what I did in the example before. Use the algebraic expansion once again of a plus b squared to expand the sigma contents. As the sigma notation can be linearized, the sigma contents can be broken into three segments, as said before. Noting that the sigma ith value minus population mean from I equals 1 to n is merely the difference between the population and the sample mean, and sigma 1 from I equals 1 to n is just n, the values can just be simplified as follows by pulling 1 over n out for the first term and using the property that the expectation of the squared deviations is just equal to variance. Taking note that the variance of x bar is merely equal to the population variance divided by the number of data values in the sample, continued simplification over here will eventually derive into equation where n minus 1 divided by n times the population variance expression is equal to the unbiased sample variance estimator. Now, to convert this biased sample variance estimator, which we used way at the start to prove how it always underestimates the variance of the sample, to convert this into unbiased sample variance estimator, which means to convert it into something that can accurately represent the variation without needing to know the population average, which is represented by mu, which is integral or essential to be calculating the population variance. We just need to divide this by n minus 1 and we multiply it by n as we have shown here, and we finally obtain an equation where without mu or the population variance we're able to convert this biased sample variance estimator to an unbiased sample variance estimator, which only requires the mean of the sample and not requiring the mean of the entire population, as mu is not really required within here. So there you have it, an intuitive explanation of how the sample variance estimator always underestimates the population variance and how the denominator needs to be changed to rectify this. This is collectively known as Bessel's correction.